Hello, ladies and gentlemen. My name is Chris. I'm from Group 1, consisting of approver Deborah, Qilin, Yulin, and myself. And we'll be touching upon the paper on impossible frontiers. This will be the agenda for today. I'm going to explain what's the concept behind impossible frontier. I will also explain some of the methodologies employed in the paper, as well as examine efficient frontiers in the case of a hypothetical 2 or 3 case scenario. Then Deborah would proceed to examine two classes of probability measures for selecting covariance matrices and show that under both these classes of measures, impossible frontiers tend to impossibility, especially when the number of assets increases without bound. Approver is going to examine the linear one-factor return generating model as well as the empirical data analysis to verify the theoretical findings. Qilin would also examine the linear one-factor return generating model and show how to construct a covariance matrix that does not yield an impossible tangency portfolio. Lastly, Yulin would critique on the paper on impossible efficient frontier. So, if we recall, what does CAPM say? CAPM said that there exists an efficient frontier of mean variance analysis. For every given level of variance, we know what's the highest possible returns that we can get. What it also says is that there exists a market portfolio, also known as the tangency portfolio, that must lie on the efficient frontier. And this portfolio is such that each asset's weight is proportional to the total market capitalization. So what CAPM, in summary, implies is that there's at least one portfolio, which is the market portfolio, on the efficient frontier with all positive weights. The author of the paper, however, realizes that in reality this is not the case. He's made two different observations. First is that in reality, given asset return parameters such as mean, variance, and covariance, the efficient frontier does not include any portfolio with only positive weights. Another way of saying is that efficient frontiers are impossible. An impossible frontier is an efficient frontier where all portfolios containing at least one negative weight component. So he's also observed that as the number of assets grow larger, the probability that the resulting frontier is impossible approaches 1. So there is a level of inconsistency between actual efficient frontier and the CAPM equilibrium, and the paper explores on this. However, before we jump into the empirical analysis, I think it's good that we run through some of the methodologies. In order to study the likelihood of an impossible efficient frontiers, we would take several steps. One is that we would determine the asset covariance matrix from a selected probability distribution class. That will be elaborated by Deborah. It can be uniform prior or linear factor model prior or other distribution class. Next, once we have the covariance matrix, we would combine that with the mean and the variance in order to obtain the efficient frontier. And once we have the efficient frontier, we're able to determine whether the efficient frontier is impossible. So it's also important to recap at this point, how do you go about building efficient frontiers? The key is to minimize this term here, which stands for the variance of a portfolio, at every given expected return, with the requirement that the sum of all weights has to be 1. So if we employ the method of Lagrange multipliers, we'll be able to build the efficient frontier. We also need to know what's the definition of impossible frontier? How do we define it or quantify it in mathematical terms? So we call a frontier impossible with respect to the ith component if the weight of the ith component at each point on the frontier is negative. So we know that every point on the efficient frontier can be written in this form. And since the value of C and D are non-negative by Cauchy-Schwarz inequality, a frontier would be impossible with respect to the ith asset exactly when omega p and omega g both have negative I components. So before we jump into the case of multiple assets, let's start with 2 assets and 3 assets. In the event of 2 assets, it's actually proven that it is possible to rule out impossible frontiers. However, in the 3 asset case, we can't do the same. The author has actually set up a study with the following class of parameters: expected return, variance, as well as covariance matrix, where E stands for the error and D is essentially 1 minus error. So given this class of parameters, we are able to determine what's um, the weights of all the portfolios along the efficient frontier by varying sigma. So we note that however sigma is varied, there will at least be one component of uh, omega which will be negative, and hence the efficient frontier corresponding to the class of parameters described above are impossible for sufficiently small values of error. I'll now pass on my time to Deborah.
Thank you, Chris. We can now move on to analyze the general case of n arbitrary assets in a portfolio. In the paper, the authors analyze the likelihood that the resulting frontier is impossible, given a vector of expected returns and a randomly selected covariance matrix sigma. In order to do so, we must first determine the probability distribution of the covariance matrices. The authors chose to analyze two different distributions. Firstly, a uniform distribution, and secondly, a class of probability distribution centered around covariance matrices generated by linear models such as CAPM and APT. For the first distribution, the uniform distribution, the principle depends on the absence of prior information, meaning that the distribution has to be uninformative and invariant. We first consider a space of all n times n covariance matrices Pn, Z a cross-section of Pn written in terms of its coordinates, and the form of covariance matrix sigma in terms of matrix products A times M times transpose of A. The distribution function associated with the uniform distribution is known as the Haar measure. Using this measure, given a randomly chosen matrix M in the cross-section Z, the probability that a covariance matrix sigma gives rise to an impossible frontier for a matrix M in the cross-section Z is bounded below by the following formula. From this equation, we can see that for any fixed value of y, the probability that a covariance matrix in a cross-section Z gives rise to an impossible frontier tends to 1 geometrically as the number of assets n increases. However, there are several criticisms regarding the use of uniform distribution, mainly because it is too general and may not yield economically relevant results. The second distribution is based on covariance matrices generated by linear factor models. Incorporating independent idiosyncratic risks into the covariance matrix, we can define the family of matrices as follows. For any given expected return vector mu, excess expected return vector mu m, market volatility sigma m, and risk-free rate Rf, we can consider phi to be a probability distribution in the family of matrices. Under this probability distribution, the probability that a random choice of sigma gives rise to an efficient frontier that is impossible is bounded below by the following formula. The authors have proven that the lower bound is applicable uniformly across all choices of phi and also across all choices of mu, mu m, sigma m, and Rf. This result can also be extended to any linear k-factor models, where the term n-2 in the formula will then be replaced by n minus k-2. So from this equation, we can see that as the number of assets n increases, the probability that a chosen frontier is impossible tends to unity. The authors have also moved on to derive three other results that characterizes short positions in the impossible frontier. Firstly, they attempted to determine the expected number of total assets n such that a generic frontier would be impossible. Under the same probability distribution phi, the expected number of the total number of assets n is given by C prime times n minus 2, where C prime is defined as follows. This formula shows that the number of assets requiring short positions in a typical frontier such that it is impossible grows linearly with the number of assets. Secondly, they tried to derive a lower bound for the expected number of short positions among efficient frontier portfolios. If we let Si to be the infimum of the short positions in the asset, measured as a fraction of the portfolio's net asset value, then the lower bound is given by Ci, where Ci is defined as follows. Lastly, the authors tried to analyze the impact of imposing short sale constraints on the probability that a frontier is impossible, and it turns out that imposing short sale constraints does not decrease the probability that a frontier is impossible. So if an unconstrained frontier is impossible, it also means that its corresponding frontier FB is also impossible. I'll now pass the time on to Apurva.
Thank you, Deborah. Let us now consider the one-factor model. The following is the linear one-factor model that underlies the CAPM, where return on asset is given by risk-free rate plus beta times the return on market minus the risk-free rate plus a term called epsilon, which is in fact market shocks, or simply the error term in the regression equation. Now over here the assumption is that the expectation of epsilon is 0 and the covariance matrix for the same is represented by omega. Also, we can calculate the mean vector mu and the covariance matrix sigma of asset returns by taking expectation and variance of the same equation and receive the following results. Now, we have seen in the previous slides that the tangency portfolio for the above equation is in fact given by the following equation, which is sigma inverse mu by b. But there are two assumptions under which this is in fact possible. The first is that mu contains all positive terms, which is to say that there are no short positions in our portfolio. And second, that rho is in fact diagonal. That is, all the covariance error terms, the covariance between the error terms is in fact 0. However, if we do away with these assumptions and consider that the covariance matrix is more general, which is to say that there is some covariance between two error terms and there are no constraints on mu, that is, we can have short positions in our portfolio, then we see that impossibility is in fact the rule and not the exception. The calculations for the same are not covered in the slides but are there in the paper, and it in fact states that you can calculate a covariance matrix for the impossibility frontier using change of coordinates and then calculate the lower bound of the probability for the same, which in fact shows that the bound is quite close to 1. Again implying impossibility of the frontier. We will now move over to empirical analysis. The following shows empirical illustration of our theoretical findings using daily and monthly returns of S&P 500 for last 25 years of data. Here we have plotted the efficient frontiers for the first 100 assets for daily and monthly returns respectively. The thin line over here represents the unconstrained frontier and the thick line represents the frontier with at most 50% short selling allowed. And we see that the sample estimators do yield impossible frontiers again. This means that negative holdings are in fact the rule rather than exception for efficient frontiers, which we have shown empirically. And this also implies that constraints for non-negativity are likely to have a major impact when we optimize portfolios using the mean variance technique. Now, since we are considering empirical analysis, we should talk about estimation error as well. One might give a critique that estimation error might actually yield the mean and covariance matrix to be inconsistent with CAPM. But while doing practical portfolio management, we must always estimate the portfolio means and covariance matrices, which is to say that there is no way to avoid estimation errors when applying this method. So we do not really make any adjustments for any estimation errors to our model. Coming to the conclusion, we see that mean variance efficient frontiers are almost always containing short position. This implies a fundamental inconsistency between efficiency and economic equilibrium established by the CAPM, which is to say, if a portfolio is mean variance efficient, it is bound to have short positions as well. This is actually shown in market by a huge surge in the use of long short strategies, where portfolio managers in fact prefer to take both long and short positions when optimizing portfolios using mean variance frontiers. Even in an ideally frictionless world where all parameters are known and fixed and all the other perfect market assumptions of the CAPM hold, mean variance efficient frontiers are almost always impossible. And also, this shouldn't be too surprising that the likelihood of simultaneous equality of supply and demand across number of markets is small. increasingly less likely as the number of assets grow. That's about it for this paper, and now Yulin will be covering the next paper, which is about the commentary on impossible frontiers, which is in fact a reply to the impossible frontiers. Thank you.
Thanks, Apurva. Now it's my turn to talk about the replies to the impossible frontiers. So first, let's have a quick recap. So a portfolio is called impossible if every asset in the portfolio has negative returns. This goes against the CAPM model, which assumes that every asset should have a positive weight in the portfolio. And also, as the number of asset n increases, the probability that this portfolio is impossible is approaching to 1 at a geometric rate. There are a lot of critics to the paper published. One of them, Levin and Rowe, says that such possible portfolio, there are many of them, is very common. But we can prove it that this is the possible portfolios are indeed rare. And also, it occupies an isolated region of the mean variance parameter space that becoming increasingly remote as n increases. Also, Ingersoll says that the parameter restriction can be ruled out based on some other restrictions. But we can prove that in many cases, these restrictions contradict the empirical fact and must be questioned before we really blindly using them. So based on the Levin and Rowe, their comment is focused on the robustness of our main conclusion, that if we fix the vector of expected return mu, a randomly selected covariance matrix will always produce a negative mean variance frontier portfolios. And these portfolios are impossible against CAPM. However, LR's contradiction is that parameter sets leading to possible frontier resemble like rational numbers. You can see that the probability of a random sampling number to the real number line is 0. But on the real number line, you can always find a rational number nearby as close as possible. For example, pi is not a rational number, but however, within this region pi minus epsilon and pi plus epsilon, we can always find a rational number no matter for any small enough value of epsilon. But based on my research, we can see that the possible portfolio is not only rare, but fall in a very well-defined and localized region of mean variance parameter space, unlike rational numbers on the real line. So basically, LR's approach is trying to solve for a set of parameters mu and sigma, which use a possible frontier that's close enough to the sample estimator of this mu and sigma under certain metrics. It seems suggestive, but it's not really a proof in a formal math sense. The region of the possible frontier weight, we can see that it is the linearly mapped to a multiplication of this covariance matrix to an open corner with a single connected component in mu space. And this corner of the parameter has positive mass. Now there are more parameters of this type than in the rational numbers. We can show that the probability to find a possible portfolio based on this is 0. And for 100 assets, the likelihood to join an impossible frontier is 99.66%. Nevertheless, determining a particular region of parameter space that do yield a possible portfolio is still worthwhile exercise. We propose a simple, general, and most consistent method based on Black and Litterman's framework, and we will attach it later. The difference of my approach and LR's method is generally that ours is a theoretical result that holds in general, like LR's report is an empirical result that may or may not be generalized. Also, LR fixes the covariance matrix and varies the asset expected return variance, Well, we fix the expected return and vary the covariance matrix. However, our approach can be easily be applied to the expected return vector. So now let's welcome Yulin for her critiques from some other perspectives. Thanks.
Thanks, Jilin. Subsequent to the LR's critiques, X also have his perspective on the results of author's paper. So there are two major parts that the author mentioned in his reply paper. The first one is literature parts that ICSO focus on the theoretical restriction that rule out the impossible frontier. So he doing this by providing an example that if there is no restriction on the underlying parameter to yield positive, the complete market always have arbitrage opportunities. So ICSO also provides some technical analysis to prove that the frontier in question is possible. He doing this by the beginning with the premise that the vector of price is equal to this parts and given the random value of positive value of A and B. So after this, we can easily get the capital P, which is the diagonal matrix of a price. Then after this, we can easily get the mean return and the covariance matrix. We can also change the equation into this format, and based on this, and according to the assumption that the value of H is random and positive, we can always get easily get the results that the omega 1, which is the portfolio, will always lie on the efficient frontier with all the elements weights is positive. So therefore, a portfolio omega 2, which is proportional to omega 1, will definitely lie on the efficient frontier according to all the parameters. So regarding all the arguments that for ICSO, the author replies as follow. The first is the philosophy difference. The theorists often asserting that equilibrium must hold under any circumstance and irrespectively of the empirical evidence. However, the writers argue that the theories is meant to be approximation of the complexity of reality. So what they need to do is focus on the magnitude of approximation instead of other parts. So the second is also reply according to the technical analysis. At first, they agree that omega 2, which is proportional to omega 1, is still lie on the efficient frontier only if based on the condition that B minus 1 is less than B over C. Then what's more important is that they may have some circular arguments, which means if you assume that all the elements of H is positive, is equally to mean that all the elements of weights are positive in omega 2. So besides these two, the author also mentioned about the literature reference. So they claim that what they do is based on a given mean return and the covariance. After this, they based on the parameter is never to get the portfolio that lies on the mean with portfolio that lies on the mean variance frontier. So besides that, the author also mentioned some common grounds with these two authors. The first is that the CAPM is specialized parameterized, which impose many restrictions on the market variable. However, what we need to do is to make proper use of CAPM instead of discarding it totally. So the author also provides some explanation that the inconsistent between CAPM and the empirical observations are more fundamental instead of just estimation error. So this should be pay more attention to our project managers or portfolio managers to re-evaluate the CAPM results. So for those financial data and the institution details, the authors also provide that they will have some develop greater respective for this empirical evidence phenomena. So that's all for our presentation. Thank you.